Yeah, so maybe I can start by introducing this seminar series where you are the first, Igor, are the first lecturer. So we have, by this, we are initiating a series of seminars on transport properties, and which we think can be of value for WWSC, but also for in general for all the research groups and so in Linköping and Chalmers and Stockholm, KTH and so on. The idea is to keep it on a level that we can all we who are not experts on for example, electric transport can learn things from this, which we can benefit of later on, or soon maybe. So this is the first lecture by Professor Igor Zozoulenko. Next one next month, it's me on small molecule diffusion and barrier properties. And then we have Professor Annette Larsson in December, who will talk about controlled release. The idea from my side was to start with something very small that is transported, and then we go to larger things, ions and small molecules, and then go up to larger and larger species that are transported. For technical reasons or practical reasons, a lecture on ions will be after Christmas sometime. And we are very happy to have Professor Igor Zozoulenko to do this for us as an expert in this. You are currently in the Laboratory of Organic Electronics at Linköping University, where you had a research group. We have a lot of, we expect a lot from you now, because you apparently got what is called Gyllene Moroten 2005 from your skills of teaching. So that puts, that would, so we expect a lot today. Thank you. But yeah, please. I think.
Okay, thank you very much.
We can start.
Can I just say something? So I think for the setup for this seminar, I think it's easiest if you have questions during along, maybe you can put up your hands or post them in the chat, and then Igor can also see them. And we can have, I guess, Igor, maybe you want to take pauses from time to time to look if you have questions, or what do you want? Do you want someone who has an immediate question to raise their hand and make you aware in some way, or how do you want this to happen?
Yeah, actually, sometimes I can actually miss questions in the chat when I simply could not, sometimes might not see them. So if people just unmute and interrupt and then ask question, it would be perfectly fine.
Okay, but if there are not immediate questions, then you can post them in the chat.
Yeah, and then please post in the chat. So the idea is that there will be two talks, like 2 academic hours, 45 minutes. Yes, and then we will make a break, 15 minutes between the hours. Okay, so then I will start. So just a very brief introduction of my group. So I am head of theory and modeling group. So this is our group. And I will try to just a second. So this is our vision. Yeah, as you know, material science is dominated by the experimental research, and in particular trials and error methods, when you try and then make error, try again, achieve success. And basically our vision as a theory and modeling to basically replace it by this like streamlined compute, try and then go to success. So what we do, we are providing fundamental understanding of structure property relationships, in particular answering questions why, how, etc. So for example, the typical title of our paper can be, why does solvent treatment increase the conductivity of P dot PSS? So this type of questions that you cannot answer just doing experimental research. You really need to go deep into the theory and modeling. And of course, we provide simulation modeling of devices and materials to guide and interpret experiments. Okay, so in terms of materials, we work with soft materials, basically with conductive polymers, with wood-based materials, with macromolecules. And so in this plot, I showed the scale, phenomena, and methods that we use. So basically, our research covers all the scale, started from angstrom, going through nanometers, sub-micrometers, and millimeters. And this is on angstrom scale is electronic structure, optical transitions, redox reaction, and here we use DFT, for example. On this scale, nanometer scale, it's basically morphology, electronic and optical, and ionic transport, where we use molecular dynamics and various transport calculations. And also we do device modeling, where we use so-called drift diffusion equations or Poisson-Nernst-Planck equations, which is another word for this. Okay, so and now what to expect from this lecture? Well, to me it was a challenge, because when I tried to prepare it, I tried to find a compromise between several following things. So first, this lecture is supposed to be given to Wallenberg Wood Science Center PhD students, who most of them have background in material science, chemistry, biology, but electron transport is mostly physics. So therefore, I had to kind of adjust the level of the presentation to background of most of the people. Also, the stuff that I'm going to talk about is quite advanced. It contains quite advanced concept. And actually, I counted. I will mention 11 Nobel Prizes during this lecture, which kind of addressing particular aspects of electron transport. And this is an enormous field to cover in 2 hours. And of course, in this lecture, I will give my perspective on how kind of I see it. So basically, as I said, so this lecture will be a compromise between all these factors. And again, as I said, please free to interrupt and ask questions. So this lecture, very briefly outlined, it basically would consist of 3 parts. So first, I will start with the main definition and concepts, then briefly go through thermoelectrics, and then I will discuss the types of electron transport: band transport, Hopin transport, and quantum transport. And then, so this will be kind of a first part. Then, in Wallenberg Wood Science Center, we mostly deal with soft materials, and a lot of people work with hybrid structure, various wood-based system and conducting polymers. So therefore, in this lecture, I will focus on conducting polymers. And so here I will consider Hopin transport and conducting polymers. So in the second part, I give a brief introduction to conducting polymers, because in order to describe electron transport there, you need to describe the system first. And then in the third part, I will consider 2 case studies. One is the Monte-Carlo calculations of the temperature of the conductivity, and a second case study is a multi-scale mobility calculations in conducting polymers. Okay, so I will start with first part. As I said, first part is general concept and types of electron transport. Okay, and then I really will start with really basic things. So of course, current, you defined how you define current. Suppose you have a conductor, then you have some surface, and then current is defined as a number of charges transferred through the surface in unit time, and therefore unit of current is ampere, which is 1 coulomb per 1 second. Okay, then if you take a resistor, and then if you apply voltage to this resistor, you will find that the current and voltage that are proportional to each other, and this proportionality coefficient is called the resistance. Or unit of resistors. Resistance is ohm, And resistance is given by this formula, so it's proportional to the length of the conductor, inversely proportional to the area, which is a geometrical factor. But also there is this material parameter rho, which is called resistivity. And if you take inverse of rho, it's called conductivity. And this is material parameter, and it's different for different materials. And this is basically the kind of ultimate aim to research in electron transport is to calculate or measure or understand the conductivity of the system. So basically current locally is defined, or this current density is the conductivity multiplied by electric field, and electric field is a gradient of minus gradient of applied voltage. Okay, so next step, again, I will go through really basic things. I will introduce this very basic concept, call it drift velocity, mobility, and conductivity. So I start with the drift velocity. What is this? Okay, so suppose you have a conductor like this. You place a conductor in the electric field. You apply electric field, and then you would like to trace the motion of an electron. So what you do, you write down Newton's equation of motion. Very simple. You solve this equation of motion, where force is basically charge Q multiplied by electric field intensity. And then you find that velocity would be given by this expression, Q multiplied by electric field intensity E divided by mass and multiplied by time. Okay, but then if you start thinking about this expression, you will find that in principle, if you make kind of apply voltage for long enough time, your velocity will grow linearly. So in principle, if you wait long time enough, it would go to the speed of light or something like this, which does not make sense, of course. And this means that in a realistic system, in a real system, this picture is too simplified. What is actually going on? When electrons move inside the conductor, there are a lot of scattering. We will talk about the origin of the scattering later on. So this means that in principle, in this formula, what you should do instead of time, you should substitute this time by some average scattering time, which is basically the time between two different scattering events. And then doing this, you can write down that velocity is equal to some constant multiplied by electric field. And this constant is called mobility, and the velocity, this velocity would be called drift velocity. So basically the drift velocity is a velocity when you apply electric field. This is a velocity where with what your electrons move inside the conductor. And actually this drift velocity is very low. For example, for copper wire, it's just 23 micrometer per second, extremely low. Okay, so here, we are introducing these two basic concepts, drift velocity, mobility. And then next concept, probably one of the most important one, is the conductivity. And the conductivity is given by this expression. So as I said previously, conductivity relate current. In this diagram, so conductivity relate current density and the applied field. And so one can show very easily, so it's an undergraduate electricity course, that conductivity is given by this expression. So it's the charge multiplied by concentration and multiplied by mobility. So for the conductivity, it's not only the mobility which matters, how fast electrons would move, it's also the electron density. So the larger electron density, the larger the mobility you have. Okay, and if you look at different materials, you will find that conductivity extends in the huge value, huge region, like from 10 to minus second Siemens per meter to 10 to minus 16 to 10 to 8. So it's a huge variation. And basically all the materials divided in kind of three categories. Conductors in this range, semiconductors, and insulators. Okay, And then you can ask, why are different materials have different conductivities? And one of the answers to this question, it's different materials have a different character of atomic bonding. So let's then take a look in more details on character of atomic bonding. We have three types of bonds: ionic bonds, covalent, metallic, and secondary bonds. So let us start with ionic bonds. Ionic bonds is typically bonds in the materials with two different types of atoms: electropositive atoms that can give up their valence electron easily, and electronegatives. They can accept electrons very easily. And the classic example is the salt, sodium chloride. What is important to stress that ionic bonds are non-unidirectional, and also there are no free electrons there. So basically, electrons kind of stays where they are. They cannot move freely. Second type of bonds is the covalent bonds. In this case, you have, for example, here two atoms, and then both atoms can have unpaired valence electrons, and these two valence electrons, they basically form a bond. And these bonds, as you can see, they're directional. So basically, electron density is localized between the atoms. And also in this case, there are no free electrons. All electrons stays close to the atoms. Here is some example of crystalline silicon. Okay, and next type of bond, secondary bonds. These are hydrogen bonds and van der Waals bonds. For example, for hydrogen bonds, it's water is the best example. Water forms a permanent dipole, and then negative charge is here concentrated on oxygen and positive on hydrogens, and then basically you have this dipole-dipole interaction forming the hydrogen bonds. But many materials, they don't have permanent dipoles, but dipoles can be introduced there. For example, here this picture shows how the dipole is introduced. So you have the motion of electrons and nuclei, and at any given particular moment, you have kind of dipole, which magnitude changes all the time. And basically, the interaction between these dipoles provides a dipole-dipole interaction and creates a bond. And for example, graphite is a very nice example. So you have like this weak van der Waals bonds between the layers and strong covalent bonds inside the layers. But again, in this case, you also don't have any free electrons. All electrons stays within atoms. And finally, we come to the metallic bond. Metallic bonds, they form by metals, and so actually most elements in periodic tables are metals. And then where outer valence electron can be easily detached from the atoms. And then what we have here, we have a positive ions that form basically the kind of back scaffold of one can say of this metal. And then we have free electrons moving and delocalized electrons moving between them. And apparently, this structure, this type of materials can support electrical conductivity because of the free electrons. This diagram, this pyramid shows you kind of these 4 different type of bonds: metallic, covalent, secondary, ionic. And these are different type of materials which corresponds to these bonds. So for example, semiconductors are typically covalent bonds, metals, ceramic and glasses, it's somewhere in between covalent and ionic bonds, and polymers, they're somewhere here. Okay, so this is kind of looking at the bonds is one way to look at the origin of conductivity, electron transport in metals. However, all modern theories of electron transport, they are based on band theory of solids, which of course was related to the character of bond character. So here I will try to introduce you very quickly to the band theory, and then we will classify different conductors based on the band theory. Okay, so if you start with just one atom, we calculate the energy levels, and according to quantum mechanical calculations, we know that electrons are populate discrete energy levels. And here, for example, I depicted the highest occupied energy level, and this level is lowest empty level. Okay, now suppose these two atoms make a dimer or molecule. What would happen? So because of the interaction, basically you will have now these two levels, which are, so there is some splitting between these two levels, and again the same happens with the lowest unoccupied level. And then we basically continue. If you have a nanoparticle, so we will have a picture like this. So here we have many levels. Basically, not many number of levels is equal by the number of in this case, nanoparticles, which are occupied by electrons, and here the empty levels. And finally, when you go to the solids, when we have a crystallic solid, so all these levels, they kind of emerge into band, which is called valence band. And in valence band, all states are filled by electrons. And all these empty levels, they kind of collapse into the so-called conduction band, where all states are empty. And there will be energy gap between the valence band and conduction band. Okay, and now we can classify all the materials according to the energy gap. So if the conduction band and valence band, they don't have any energy gap, or very often actually they are overlapping, we have a metal. If this energy gap between, say, 0.13, it's a semiconductor, and if it is more than 3, it's insulator. Okay, now the question is why does the presence of the energy gap lead to the low conductivity? Why do we have isolating behavior in the case when we have energy gap? Okay, and the answer to this question is pretty simple. Okay, so let's take a look at the semiconductor. So first, let us notice that thermal energy of an electron at room temperature is this 0.025 electron volt. This means that in order to kind of push electrons, you need to give some energy. Just electron acquires some velocity. Okay, but look here, all states are in valence band, they are occupied. So you basically to give the electron additional energy, you can move it in the higher lying state in the energy. But available state here is at the distance 1 electron volt. And this is very big, actually, distance. And thermal, because it's much larger than this thermal energy. So of course, according to the Boltzmann distribution, there will be some electrons that you can put there, but the number of these electrons is very small, but still non-zero for the case of semiconductors. So therefore, the conductivity will be very low. However, for the case of the metal, look here. Here are filled states in the valence band, but conduction band is overlapping with the valence band. So, and conduction band, there are a lot of empty states. So basically, this thermal energy, it would be enough to move electrons from the valence band into the conduction band, and then when you do this, so electrons can move inside the crystal. Okay, and for the case of insulator, this gap is so large that the thermal energy is not enough to fill conduction band, so practically your conductivity will be equal to 0. Okay, so this was the classification of the conductors, semiconductors, and isolators based on the band structure. And here I would like to introduce another concept, which is called density of states. It's maybe not very difficult concept. It tells you how much states you can put into your, how much electrons you can put into your system at the given energy. And this is quantum mechanical quantity, because kind of classically, for example, classically, in principle, you can charge your system as much as you can. But in many quantum mechanical systems, it's not the case. So here, for example, basically density of states tells you number of states in the interval dE. So for example, here you have some interval, and basically this tells you how much states you would get. And these two curves shows typical profile of the density of states. So here at the band H, so this is the bottom of conduction band, so density of states is 0, and then it starts increasing. So you can put more and more states there. Okay, and finally, concerning band structure, I would like to discuss the case of doped semiconductors. So yeah, as we just discussed it, in principle, semiconductors, or if we call them intrinsic semiconductors without dopants, they don't conduct electricity very well. But then what you can do, you can actually dope semiconductors. And this is what people do in the semiconductor industry. Because of this, you basically you can have all semiconductor devices. And therefore, we can say that we live in this silicon age. So what is this? So first, suppose, here this picture represents so-called intrinsic semiconductor. Intrinsic means that there are no any dopants. So here is the case of silicon. Silicon has valence 4, so each silicon has 4 valence atom, and then it forms a bond with the neighboring atoms. Okay, but now suppose we substitute one silicon with one phosphorus atom. So phosphorus atom has a valency 5. This means that there is one extra electron. So all 4 electrons will make a bond to silicon, but one electron, what would happen to it? It would be free. It would be freed, and this electron can move around. And in terms of the band structure, so this is how the band structure looks like. So when you add phosphorus into silicon, so here you add one more band corresponding to the phosphorus, and this is the corresponding density of states. And basically, in terms of the band structure, you can basically kind of put the electrons from this band into the conduction band of silicon, and this would provide you free electrons which can move inside the crystal. So, and these are called n-doped semiconductor, n from negative, such that the charge carriers here are electrons. Another case is so-called p-doped semiconductor. It's a positives. In this case, let us consider that instead of phosphorus, you have a boron, and boron has only 3 valence electrons. So this means that there will be one bond not formed, and such kind of not formed bond would correspond to the hole. So it would correspond to the kind of quasi-particles that we will call hole, positively charged quasi-particle corresponding to the absence of electron. And basically, this kind of absence of the bond can jump around the crystal, and we say that this is quasi-particle hole jumps around the crystal, and provides a positively charged quasi-particle moving in the crystal. And in terms of the band structure, so here is a band corresponding to this boron dopants, and this is corresponding density of states. So, and this picture schematically show you that you can add positively charged holes into the system. So basically you can start, or in other words, you basically remove electrons from the valence band, or in terms of kind of a language of semiconductor physics, you add positively charged holes. Okay, Now let's move further. So I believe that now I am done with kind of basic concepts like mobility, conductivity, band structure, and then I move to thermoelectricity. Why I mentioned thermoelectricity here? Because I know that in Wallenberg Wood Science Center, at least in Wallenberg Wood Science Center 2, there were quite a few people worked with electricity, for thermoelectricity, for hybrid system, composite of cellulose and conducting polymers. Okay, so what is thermoelectricity? Well, kind of in most applications, you generate current by applying potential difference. But it's not only way how you can generate current. You can generate current in some other ways. And one of the way is you can apply temperature difference. And then when you apply the temperature difference, there will be a kind of motion from hot to cold. Also, you can apply, you can generate current, for example, if you manage to generate concentration difference, concentration of electrons. So then you will have a current from high concentration to low concentration. Okay. And but then we now discuss in thermoelectricity. So when we apply the temperature difference, so this gradient of temperature, we will see the current, and this was discovered by Seebeck, long time, 200 years ago actually. So basically, the first term describes the generation of the current due to the applied potential. So this is conductivity multiplied by gradient potential, this minus, and this is current generated by the gradient of the temperature, and S, Seebeck coefficient, tells you how efficient this generation is. Okay, and then based on this effect, what you can do, you can construct a so-called thermoelectric generator, or sometimes it's called thermoelectric leg, because it looks like a leg. So what you have here, you basically have here, you have a source of the hot. So this is hot. You apply hot reservoir. Here is the cold reservoir. And here you have two types of material. One of the material is a p-type, where the charge carriers are holes, as I just discussed it. And another one is n-type. And the direction of the motion of charges, they all go from the hot to cold. And it does not matter whether the electrons or holes. However, the direction of the current is different because electrons and holes have different charge. The direction of the current is different. So therefore, when you generate a system like this, the holes, electrons will go in this direction, but holes will go in this direction. So this means that you can create a circuit like this. And then this means that you generate current by applying the temperature difference. So this is one leg, and you can combine this leg in this thermoelectric model. You can put many legs such that you can put them in series, such that you can generate large voltage. And then you can use these thermoelectric models in many different applications. And basically the applications for this would be in the system where you don't need, or for some reason you don't want to have any moving parts. So here you don't have any moving parts. So basically you apply hot and you apply temperature difference and you generate currents. And this is some examples where actually people use thermoelectric generators, like off-grid power generators, and then Mars Curiosity rover, they use thermoelectric generator. Okay, an interesting question, what kind of materials are good for generation of, what kind of materials are good thermoelectrics? As we just discussed conductivity, apparently it's the metals who have good conductivity. With thermoelectrics, it's a bit different because you can show, I will not go into details, but you can show that efficiency of thermoelectric generator is determined by the so-called figure of merit. And in this figure of merit, you have a sigma electrical conductivity in nominator and thermal conductivity in the denominator. And this unfortunately creates a problem. So for example, if you take a metal, so this means that you have, in order to have a good generation of thermoelectricity, you have materials with a high sigma, high conductivity, but low thermal conductivity. Unfortunately, if you take a metal, it would not work, because in metals you have both high thermal conductivity and high electrical conductivity. Ceramics would not work because, yeah, they have high thermal conductivity by low electrical conductivity. Yeah, plastics also don't work. So therefore, you have to find materials which have simultaneously high electric conductivity and small thermal conductivity. And there are not so many materials which satisfy these requirements. There are some inorganic materials like those, but also there are conducting polymers actually can satisfy this requirement, and therefore there is an interest to thermoelectricity within community, people working on conducting polymers, and also, yeah, as I said, people in Wallenberg Wood Science Center. Okay, and then finally, let us now discuss the types of electron transport. So in principle, we can define 3 different types of transport. It's first band transport, Hopin transport, and also quantum transport. Actually, within quantum transport, it's a really broad. There are many different kind of mechanisms for transport. But anyway, let us start with the band transport and Hopin transport, which are kind of basic concepts in the electron transport. Okay, so what is the band transport? Band transport is a transport where you can see in metals and also in doped semiconductors. And the mechanism of the band transport, it's an electronic state extended over the volume of the material. So here I illustrated this like you have a valence band, you have conduction band, and then, as I said, in metals, electrons can be filled, so can be kind of filled in the conduction band. And basically, these are electrons in conduction bands, they are responsible for band transport. Also, in electronic transport, there is a very important concept, I call it Fermi level, and Fermi level determines your energy level up to which electrons are filled in the conduction band. Okay, and band transport is typically, very often at least, is described by so-called Boltzmann equation. And Boltzmann equation, in my opinion, is one of the most important equations in physics. It's like Maxwell's equation or Newton's equation. So this is it has probably the same importance in transport phenomena, but also in many fields of thermodynamics. Okay, so this equation for distribution function, and it looks like this. And there is this term which is called collision term, which describes the scattering. I mean, this term looks very simple, but it's, believe me, its calculation is extremely complex. But basically, this term tells you what kind of scattering you have in the system, what basically determines the conductivity. Okay, so when you calculate this collision term, when you calculate the scattering, so suppose you consider electron wave packet propagation in an ideal periodic crystal, and when you calculate this quantum mechanically, you will find really astonishing result that you will find that quantum mechanically there is no scattering in this case, which means that this would correspond to zero resistivity. And this means that basically resistivity in the system, as we discussed previously, is determined by kind of non-ideality of the system, like impurities, dopants, defects, etc. Okay, so yeah, so scattering on impurities, dopants, and defects, this is one of the most important mechanisms of the scattering. And so basically, if you have a wave packet, it kind of scatters off the impurity. And this determine, this is the reason for resistivity of the system. And when you measure, when you calculate the temperature dependence or measure conductivity, you will find that this does not depend on the temperature. Okay, second important mechanism of the scattering is the scattering on lattice vibrations. So any crystallic structure can be considered as atoms, as springs, which kind of moving all the time. And in solid state physics, there is a concept, so-called phonons. So phonons is a quasi-particle describing the collective atom vibration. So this is just illustration of these photons. And we have electron scattering on phonons. So when again we have this wave packet, and then when they encounter kind of phonons, which are present all the time at final temperature, they will scatter off these phonons. And when you look at the temperature dependence of the conductivity, you will find that the conductivity decreases with the temperature. And this is a very natural result, because the larger the vibrations of the lattice, of course, the stronger will be scattering. So to summarize, if you look typically on the conductivity of the metals or highly doped semiconductors that behave like metals, this would be typical temperature dependence. At low temperature, this conductivity is impurity dominated, does not depend on the temperature. And then at higher temperature, conductivity increases. Okay, so this was basically the band transport. And now I will go to the hopping transport. Mechanism of the hopping transport. Materials for the hopping transport are amorphous semiconductors, polycrystalline and disordered solids, and the conducting polymers. Okay, and mechanism, as I said, hopping or tunneling of electrons between the localized states. And here I would like to kind of acknowledge the contribution of these people, in particular Philip Anderson and Sir Neville Mott, in basically kind of understanding the origin of the hopping transport in disordered semiconductors. Okay, and for those who forgot, I just a reminder what tunneling means. In classical physics, if you have a particle and the particle encounters the barrier, it would be kind of reflected from the barrier. It cannot penetrate the barrier. However, in quantum physics, particles should be considered as waves. So therefore, when particle encounters a barrier, there will be slight, very small, but non-zero probability that the quantum particle will penetrate this barrier. Okay, so what happens with the with the hopping transport? So it's the following. So this picture, upper picture, represents ideal periodic structure. This is exactly what we discussed. So we have a wave packet, which in principle would propagate without any scattering through ideal system. However, imagine that instead we have a disordered solid. And this energy profile shows us energy structure of the disordered solid. So instead of this nice periodic structure, you have very disordered, very disordered structure. And what happens, according to the quantum mechanics, you will see that the states, electronic states, will be localized here in this, due to this potential profile. And then what would be possible? So electrons can jump between these localized states. Okay, and then one can ask a question: what actually determines the kind of efficiency of the hopping? Where does the energy come from? So, for example, if you have electrons sitting here, it has to jump there. So you go up in energy. So where does the energy come from? And actually, the answer is that the energy comes from the thermal vibration of the lattice. And therefore, the temperature, if you look at the temperature dependence of the conductivity, it would look like this. At low temperature, it will be very small because there is very little thermal vibrations, but then it will increase with the increase of the temperature. Okay, and this means that when you study some material, and then when you look at the temperature dependence of the conductivity of this material, based on the dependence, like whether if conductivity increases, you immediately make a conclusion that you deal with the Hopin transport. And then if conductivity behaves like this, you make a conclusion that you deal with the metallic or band type of transport. Okay, so I think it's now time to make a break. So then I suggest that we take a break, and then let's be back at, let us say 3 o'clock.
Thank you very much, Igor. Yes, we do that.
So shall we start?
Good idea. Thanks.
Okay, so I will continue my lecture. Now I would like to discuss quantum transport. So quantum transport is basically a transport regime where quantum effects are to larger or smaller extents are essential in electron transport. And one of these, maybe one of the first examples, it's a so-called Esaki diode or resonant tunneling diode. And it was a subject of the Nobel Prize in 1973. So Esaki resonant tunneling diode is based on so-called resonant tunneling phenomena. And this is how it's implemented. So we have a so-called semiconductor heterostructure, which is basically here composite of the different semiconductors, 2 different semiconductors, in this case, gallium arsenide and aluminum gallium arsenide. So the difference between them is that, so here in this energy diagram, I plotted the bottom of the conduction band. And you can see here that aluminum gallium arsenide, its bottom of the conduction band is higher than gallium arsenide. This means that this material would be a barrier for electrons which are residing here in the gallium arsenide region. Okay, so what happens here? So you have the electrons here, and then you have this double barrier with empty space. Okay, and I presume that all of you studied quantum mechanics or at least modern physics, and you know that if you have this, so kind of this is textbook quantum mechanical particle in the box problem, where you have kind of discrete levels in this quantum mechanical box. So these energy levels are quantized. So this means that energy levels inside this barrier, so here I draw them, they are quantized level. And resonant tunneling phenomena is the phenomena is that when energy levels are aligned, so basically you will have a transition, complete full transition through this system. So what happens here? So in this case, what happens? You apply voltage between the left and the right part, and then this applied voltage kind of change all the band diagram. And what happens here, one of the quantum mechanical levels here, at 0 voltage it is here, but at applied voltage, it gets aligned with the energy of electrons in the reservoir here on the left side. And this means that now, because of this phenomena of resonant tunneling, the transmission probability through this system will be equal to 1. So electrons start flowing. And this is when you look at the current voltage characteristics of this diode, you will see the increase of the current. But then when you apply further voltage, basically this level will go down and the condition of resonant tunneling disappears, and then current decreases. So basically here you will have a typical diode behavior with a negative differential resistance, and this behavior is based essentially on the quantum mechanical resonant tunneling effect. Then a very interesting case of quantum transport, not very interesting, but extremely important, is quantum transport is semiconductor heterostructures based on the two-dimensional electron gas. And the importance of this structure was recognized in Nobel Prize in 2000 for people who basically developed this structure. So what you have here, you also have a semiconductor heterostructure. In this case, this is layer of gallium arsenide, as a doped aluminum gallium arsenide, again aluminum gallium arsenide, and gallium arsenide. Basically, what happens because of some electrostatics and the structure of this conduction band, what you have here, and the surface, as this surface, you will create a state which is called a two-dimensional electron gas. This means that you will have this electron gas residing at this interface. And this interface is, in principle, is a perfect interface. There is no any impurities there because kind of dopants situated kind of far away. And therefore, in such a system, you have this two-dimensional electron gas on the surface, which extremely high mobility and extremely high conductivity. And then using this two-dimensional electron gas, you can create various structures. For example, if you put metallic gates on the top, and then you apply negative gate voltage, what you will do, you will kind of remove electrons underneath the gates, and then you can create channels inside your structure. So the kind of electrons can go only in these channels. So here's some example, and this example is called quantum point contact. So basically, this is heterostructure. So here is this two-dimensional electron gas that I just mentioned, and here you put metallic gates on the top. You apply negative gate voltage. So basically, here you created a small and narrow channel such that electrons can go through this channel, say from contacts or between these contacts. And what people saw when, especially at very low temperature, so here it's a 0.3 Kelvin, they saw that the conductance through this channel became quantized. So instead of the familiar Ohm's law, when kind of current is proportional to the voltage, here you can amazingly you see steps. So where does these steps come from? And it turns out that this is a precise manifestation of the wave nature of electrons. So basically, this opening you can treat as a basically waveguide for electrons. So here you have standing waves, and basically the number of the steps simply tells you how many new standing waves you opened for electrons traveling through this channel. Okay, and then here in this picture, I showed a more complicated structure. So basically here you have not just one constriction. So here in this case, you have just one channel, one constriction. So here you can create a more sophisticated geometry. So basically here, what you do here, you create a quantum dot. So you create a space, kind of a region of space, confine it for electrons. And then, so electrons can go here, but this region is very weakly coupled to contacts, so therefore it's called quantum dot. As a matter of fact, last week when I prepared, or it was the week before, when I prepared this presentation, there was an announcement from the Nobel Prize Committee that this year Nobel Prize in Chemistry was awarded for the discovery and synthesis of the quantum dots. As a matter of fact, these quantum dots are not exactly the same as those, because one can create quantum dots differently, but the principle of creation is kind of the same in the sense that you confine electrons into confined space, and the properties of the electrons would be, kind of system would be very much different. And also why I mentioned this system is that, you know, we belong to Wallenberg Wood Science Center, but also Wallenberg Foundation funds another center, which is called Wallenberg Center for Quantum Technology, which basically aim at the building of quantum computers. And this type of quantum dots are considered as a building blocks, or one of the possible building blocks for these quantum computers. Okay, and also another example of quantum transport, very exotic one, is quantum. So now people are able to study transport through individual molecules. And so this picture represents a situation where, so you have two gold electrodes and people study electron transport through one isolated single molecule, in this case, some oligosilane. Okay, and this is my last slide about quantum transport, is that what I didn't touch at all is electron transport in high magnetic field. This is a very special field, very difficult field, and very important field. And this kind of importance recognized by 2 Nobel Prizes in different effects: this integer quantum Hall effect and fractional quantum. Okay, so now I'm done with the first part of my presentation, and I will go to the second part. Okay, so now I would like to discuss hopping transport and conducting polymers, and discuss the basically morphology and structure of conducting polymers. Okay, so conducting polymers. So this is some example of conducting polymers. One of the most kind of studied, polyacetylene, and then there are nitrogen containing polymers, sulfur containing, PDOT, which I will be talking mostly about. So yeah, as I mentioned before, conducting polymers are in principle semiconductors, and they are very, very poor conductors. However, it was discovered, it was maybe 40 years ago, or something like this, that if you dope the polymers, they become conducting. And yeah, one is that this discovery was made, as many other discoveries, by mistake. Not by mistake, accidentally. So people accidentally dope it isolating polymers, and then they found that it became conducting. But of course, this was extremely important discovery. This was recognized by the Nobel Prize in year 2000. And then today I will mostly focus on conducting polymer PDOT. And this is because PDOT, in principle, one can say it plays the same role as a silicon in semiconductor industry. It plays the same role in organic electronics. And this is because of several reasons. It has excellent stability. There are very well-established manufacturing technique. It also supports both electronic and ionic conductivity, and it has excellent optical properties. And these two plots show the number of papers on PDOT. So for example, so unfortunately, this graph ends 2016, and in this year, it was published 1,200 papers on PDOT, which probably makes it one of the most studied material on Earth. Okay, and there are really a lot of applications of PDOT. For example, cellulose PDOT composites, which can be used, called power paper, and which can be used in supercapacitors, batteries. PDOT is used in electrochromic displays. It's used as electrodes in solar cells. It uses various devices, in this case, ion pumps, drug delivery devices. Here one can actually, it's interesting work where people from LiU, they were able to kind of polymerize PDOT inside the living plant. And then the living plant was used as a supercapacitor. And very recently, this year, it was reported a wood-based transistor based on wood template filled with PDOT. Okay, and in principle, in order to understand PDOT, so it's a complex material, And depending, so basically at different levels, you can study different properties. So for example, when we go to angstrom level, we will study the origin of charge carriers, but like for nanometer levels, it's the morphology and electron transport, which is important. Okay, so this is a chemical structure of P dot. What is important here is this band bond. So this is carbon carbon back bond, and it's composed of carbon atoms in sp2 hybridization. It means, so here you have sigma orbitals, which basically creates strong covalent bonds, but this p orbital, they are situated kind of in the vertical direction, and these p orbitals, they provide delocalized pi electrons, and these electrons are responsible for electronic properties of this material and the formation of pi stacks. So this is example of kind of van der Waals bonding due to these bonds. Okay, it's very important that P dot in Hello?
Yes, you managed.
Hello, do you hear me?
Yes, you managed to fix it.
Okay. Yeah, I'm very sorry.
No problem. We got
My
the
battery, ran out of battery, and then I was trying to find a charger.
no worries.
Sorry about this. Okay. Again, do you see my presentation screen or second screen?
It's in the wrong mode.
So I have to change it, yes?
Yes.
Okay.
Thank you.
Okay, so what is the origin of the charge carriers in conducting polymers? So in conducting polymers, charge carriers are so-called polarons. So what does it mean? Well, basically, like to answer this question, you have to solve the Schrödinger equation, where H is the so-called Hamiltonian, and Hamiltonian describes the interactions that you have in the system. So you have interaction between electrons, interactions in the lattice, and then interaction between electron and the lattice, and the counter ions. I presume that I was at this overhead, right? When I stopped it. So here I just want to say that P dot is in its pristine form is oxidized, and P dot has a positive charge, and all systems in nature are neutral. So this means that if you have a positive charge on P dot, you have to have counter ions that balance the charge. And in the case of P dot, especially P dot PSS, this counter ions is so-called PSS, polystyrene sulfonate, balancing the positive charge. But also you have molecular counter ions doping P dot. Okay, so basically, origin of the charge carriers, as I said, charge carriers are polarons, and this is this term which describes very strong interaction between electrons and the lattice. So lattice, I mean the polymer chain, is in principle very flexible, and because of the flexibility, it turns out that you can get a gain in the energy if the electron charge will be localized in some limited region of space. And also what happens, you also have rearrangement of the kind of character of the bonds. So for example, in this picture, you can see a chain of P dot with one polaron localized here. Okay, and here this plot shows so-called bond length along the bonds. So black line corresponds to the neutral case. And in the neutral case, you have the aromatic arrangement. So here it's a double bond, single bond, double bond, single bond. So here, like double bond is shorter, single bond is larger. And this is called aromatic. But there, when you have a polaron, so a polaron is localized here in the limited region of chain. And you can you see here, the red line shows arrangement of the bond for charged case. And here you see a quinoid character where kind of double and single bonds change their places. Okay, so then basically what happens, you add one kind of actually take away electron. This means that you add a hole, and this hole corresponds to this state in the band, which is called polaronic state. Okay, and again, here I would like to mention the Nobel Prize in Chemistry. So all this type of calculations are done or made possible because of the development in the density functional theory and this Gaussian program, and it became possible thanks to these two gentlemen. Okay, and this picture shows how the energy structure of conducting polymer changes when you change the oxidation level, when you add more and more and more charges into the system. So for example, here I outlined one chain, and then you show one counter ion, and this means that there is one positive charge sitting on the chain, polaron. And then there is this state, polaronic state in the gap. So here in this case, you add more and more charges. So here, for example, when you have 3 states or more, so here you have more and more polarons. And finally, in the fully charged system, fully oxidized system, you have a lot of these polarons, a lot of counter ions, and these polarons, they form a so-called polaronic band inside the gap between the valence band and the conduction band. Okay, so now what is the morphology of this system? And to study the morphology experimentally, people use diffraction measurements. And there is this Bragg diffraction law. Yeah, it looks very simple, but it was a subject of the Nobel Prize. It's a son and father Braggs. And what is interesting about this Nobel Prize, William Bragg was the youngest Nobel Prize recipient. He was 25 when he got this Nobel Prize. Okay, so how do you study morphology of the system? So here you use X-ray scattering and basically use interference phenomena. So depending on the wavelengths or the distance between crystallic planes, you can have constructive interference when 2 waves going into the same phase, and you can have destructive interference when waves kind of go into opposite phases. Okay, and this is used in so-called grazing impedance wide-angle X-ray scattering. So typically, one place conducting polymer or whatever material that one wants to investigate, and then one sees the following picture. And then, so how to interpret this picture? So interpretation is rather, well, relatively simple. So, okay, so when you have, for example, if you have a periodic structure like this, you are expected to see these peaks corresponding to this Bragg scattering condition, and then they correspond to the interference, constructive interference. Okay, if you have periodicity like in both in vertical direction, horizontal direction, you will have a picture like this. Okay, and in case C, if you have kind of slightly disordered system, instead of this one, you will have kind of broadened peak. And finally, if you have kind of disordered kind of crystallic polycrystalline system, you will have the circles like this. Okay, so and this is a typical picture of GWAX of P dot. And so basically these peaks correspond to the periodicity. When you calculate this periodicity and relate this periodicity to real distance, you will see that this corresponds to the pi stacking of crystallites in the P dot. And the broadening of these peaks tells you how many chains you have in crystallites. And typically this broadening corresponds to 3-10 chains in one crystallite. Okay, now, of course, experimentally, we cannot kind of see what happens inside the P dot, but we can do it using a so-called computational microscope. This means that we can do molecular dynamic simulations to see what happens there. And the molecular dynamic simulation, kind of to give you some ideas of what you do in molecular dynamic simulations, you start with the initial system. So, for example, you put a lot of kind of separate P dot chains. You define your temperature, pressure, then you define how this change, how atoms interact, and then you start basically performing physical algorithms like tracing particle dynamics. This is what we are doing here. And basically, you start with this computational box, put a lot of water here, and basically you mimic a real process of creation of synthesizing of P dot thin films. And then you evaporate water, and finally you arrive to thin film, which looks like this in the dry phase. So basically, what you see here, you see that P dot, as many other conducting polymers, is essentially amorphous material with some limited crystallic order. So here you see some crystallites. So in this case, typically you have 1, 2, 3, 5 chains in one crystallite, and then these crystallites form so-called lamellas. So here you have kind of two crystallites parallel to each other, and this structure calls lamellas. So this would be a typical morphology of P dot, in this case P dot tosylate, but as I said, it's very typical for all other conducting polymers. And then what you can do, you can calculate X-ray diffraction pattern. You see this X-ray diffraction peak, and by the position of these peaks, you can recalculate according to the Bragg formula into the spacing. Basically, the spacing is the pi stacking. So, yeah, as I said, crystallites chains are formed in crystallites due to the pi stacking between the chains. And again, broadening of the chains, so-called Schreier equation, tells you how many chains you have in a crystallite. Okay, so this was the end of part 2, and now I proceed to the final part, where I will discuss electron transport in polymers. Okay, so I presume that I'm again not in the presentation mode. I hope now I'm in the presentation mode.
Yes. Yes. Okay, so now I would like to go through these two case studies, Monte-Carlo calculations, which are I mean, this is a very common type of calculations for disordered systems, and including conducting polymers. And also, I would like to mention so-called multi-scale mobility calculations. Yes, so yeah, as we just discussed it, polymers represent a highly disordered, or well, kind of amorphous, maybe sometimes polycrystallized system, but it's largely amorphous system. So therefore, we can expect
hopping conductance, hopping type of conductance in conducting polymer. And indeed it is the case. So this is just a reminder. So this is what you expect from metal. Temperature conductivity decreases with the temperature, but typical experiment for conductivity in polymer, it shows you increase of electronic conductivity with the temperature. And as we discussed, this is indication of the hopping transport. Okay, let's now take a look a little bit more close what is the origin of hopping transport. Again, I already showed this picture previously. So we basically have these polaronic states, and they are in principle energetically and also spatially as a disordered states, because here each polaronic states kind of feel a very different environment from counter ions, maybe from solvents, from chains. So therefore, energy difference would be very different for each of these kind of polarons or possible polaronic states. So this type of diagrams represent very well what you have in conducting polymers. So you have different states. So basically you have this hopping character of transport between different states. Okay, and this would be a model for this hopping transport. So here kind of you have different states. So for example, let us take a look at different states. I and J, they are separated by some distance in space, but also they are separated some distance in the energy kind of space. And also polymer has some specific density of states. And then, yeah, as I said, I will start with this Monte-Carlo calculation. So in this case, yeah, every polaron can be represented, or every basically hopping site can be represented by the delocalization length. So here it's a kind of length of the polaron on the lattice. And here, this is a difference, energy difference between these two states. And also, and hopping rate between two different states, in the simplest case, is given by this so-called Miller-Abrahams hopping rate. So basically here you have the exponential form, the rate, so this exponential kind of difference, exponential dependence on the distance, and also exponential dependence on the energy distance. And I would like to say that this equation is a simplified form of this very famous equation, Marcus rate for electron transfer. And so basically this equation was the subject of this Nobel Prize in 1992, given by Rudolf Marcus for his contribution for understanding electron transfer or electron transfer action in chemical systems. So in this case, basically we have an electron transfer hopping from one kind of state, polaronic state, to another polaronic state. Okay, so I will skip this one because I don't have much time. Okay, so let us now go directly to case study number 1, which is Monte-Carlo calculation for the temperature dependence of the conductivity. And the motivation, one of the motivation for this study was this paper, where people saw this behavior of electrical conductivity increasing with the temperature. And so basically here we address the question, what information can be extracted from here? Or like modeling this system, what kind of information can we extract about the charge carriers, as the nature of the polarons and kind of nature of the conductivity in this system. Okay, and so to answer this question, Monte-Carlo calculations has been performed, and here I will briefly describe the main steps in these calculations. So first, we simplify our system. Instead of this very complex geometry, we define a lattice, square lattice in the kind of simplest case. Then we apply potential difference, and here we put some kind of particles which would represent polarons, which would jump over this lattice. And we simply, to calculate current, we simply will count the number of jumps along the field and against the field. Okay, so as we just discussed, this is disordered lattice. So we start initializing the site energy. So for example, along this line, again, we consider each of this site as a possible site for polaron, and then we introduce some site energy according to the dose density of states in conducting polymers. And then what we do, we have this lattice and we place charges at this lattice according to the charge density that we have in the realistic system. And then we will use a Miller-Abrahams formula to describe these hopping rates. And then the question, how to choose, I mean, depending on kind of the distance, yeah, each particle can jump in many millions of different kind of positions. So how do we choose a hopping event? Okay, and this is why the calculations call it Monte-Carlo. Okay, so let us consider one particle. And then for this particular particle, using the Miller-Abrahams formula, we calculate all hopping rates from this side to all other sides. And then we arrange all hopping rates. And then what we do, we simply kind of throw a diamond, so to speak. And then randomly, and therefore it's called Monte-Carlo. And then this diamond will choose us the hopping event according to this random distribution. But of course, the larger the probability, the larger the hopping rate, the larger the probability that it will be selected. Okay. Sorry. Okay, as a next step, we calculate the waiting time. Suppose we selected a hopping event, but then how long time will it take for particle to jump? And then there is a simple formula which gives us waiting time distribution. And then again, we run this Monte-Carlo again. We choose some random number. We choose a particular waiting time, and that's it. So we have everything. And then we basically, using this Monte-Carlo for each particle, we trace particle motion in our system. And yeah, using the prescribed rules, we calculate current. And these are results. So in order to basically, we see that we reproduce this temperature increase, activated behavior. But what is more important, we can fit our parameters. So as I mentioned here, there are some parameters here in the Monte-Carlo technique that you are supposed to fit, where they are. Yeah, these are the parameters like localization length, broadening of the dose, transfer integrals. And from the fitting, we can extract these parameters. And this plot represents a graphical illustration of the parameters that we extracted. So we can see that according to our calculations, these quasi-particles, they are delocalized over 2-3 monomer units, and typical jump in distance would be 3-4 units. So therefore, using these Monte-Carlo calculations, we can kind of extract this, I believe, important information about the nature of electron motion in conducting polymers. Okay, and this is case study number 2. It's so-called multi-scale calculations of electron transport in conducting polymers. Okay, so what does it mean, and what is the motivation to do this? So multi-scale calculations, the aim of multi-scale calculation is to be close to the experiment as much as possible. Basically, in experiment, you start with material. So for example, here you basically start with a P dot. You synthesize P dot, then you make your measurement and you get your results. With multi-scale calculations, we want to do in principle the same. So we would like to start with particular material, P dot in this case. We computationally would like to prepare a morphology, and base it on this computational morphology, we would like to do conductance calculations. So in principle, this is a very challenging task. This type of kind of multi-scale calculation in chemistry. And this is because to do this, first we have to understand the nature of charge carriers. We have to calculate density of states, which require ab initio simulations. And on scale of nanometers, we have to calculate morphology, structure, and then we have to do the transport calculations. So therefore, they call it multi-scale. So you combine different calculations conducted at different scales. And again, the importance of these calculations were recently recognized in this Nobel Prize. Okay, so these people obtained calculations not for the electron transport calculations as I described it. It's also multi-scale calculation, but somehow different systems. It was biological systems, but idea is the same. So in order to address the property of the system, you really need to understand kind of system behavior at different levels, and then to combine them in single or in the same set of calculations. Okay, so what questions did we address in our calculations? So we wanted to understand what was the effect on the chain length on the mobility. So there is this very interesting paper published, it's almost 10 years ago, where people did here. So they collected a lot of data from maybe tens of different studies where people related conductivity of polymers to the chain length of the polymer. And basically what they see is that when degree of polymerization increases, when the chain length increases, conductivity does not change much. So it means that somehow you have this saturation. And another question is very related to this one, is the question whether we need a good crystallinity in conducting polymers to achieve a high mobility. Kind of naively, one would expect the better crystallic system you have, the larger conductivity you achieve. However, recently there were quite a few publications where people claimed that they don't really need a good crystallinity. Instead, they see very high conductivities in rather amorphous systems. Okay, so, and this was motivation to perform multi-scale calculations in conducting polymers, in this case, PDOT. Okay, so first, let me briefly describe kind of what is the kind of main blocks of multi-scale calculations. Okay, so here is the scale. So first, what we do, based on the, so first we start with the molecular dynamics calculation of the morphology. So this picture shows the calculated morphology. Then we need to calculate kind of hopping of polarons from one chain to another chain. This means, so here we need to perform calculations of these hopping probabilities, or let's say transfer integral calculations. And these are angstrom scale, and you use typically density functional approach. Also, we need some information about the structure of the density of states. So you also need to do some calculations of the density of states. Okay, and based on this, you construct so-called resistive networks, such that basically resistive network describes this kind of transport units, how the polaron jumps along the crystal. And then you do mobility calculations, and from the mobility calculations, I mean, mobility calculations by themselves are very fine, but you have to understand them. So you need to analyze them using some kind of very transparent physical picture. And this picture can be a so-called percolative analysis. So this is a general scheme of multi-scale transport calculation in conducting polymers. Okay, and then if I go like more slowly, step by step. So first, as I said, these are calculations of the PDOT field morphology. And this plot shows only backbone of polymers. So the I removed counter ions, so only backbones are shown because backbones where the electron transport takes place. Yes, then next step, each polymer, each chain kind of we consider each chain is a so-called transport unit for transport. So we basically ignore interchain motion because chains in PDOT are very short. So it's only interchain hopping which is important. So here we perform using density functional theory calculation of this hopping rates. And this is the most time-consuming and most kind of difficult or time-consuming element in the multi-scale transport calculations. Also, we calculate the density of states. And finally, doing this, we construct so-called this resistive networks. So basically, every point here represented transport units, and all these connections represent the connection between them. And then what we do, we use the master equation to solve this system, or kind of connecting transport units through these hopping integrals. And finally, this is our results. What we see here, so there are three curves. They correspond to different water content, but let us just focus on the dry sample because we don't discuss water dependence. What we see here, we basically see qualitative behavior very similar to what people see in experiment or kind of analyze an experiment. So mobility for short chains are very low, and then it decreases. And finally, when PDOT chains becomes relatively long, it saturates. So we are happy that we reproduce the experiment, but it's not kind of the most important part is to understand this. And as I said, in order to understand this, we performed so-called percolative analysis. Because of the lack of time, I cannot really go into details. So basically, I jump directly to the conclusion, which is visualized here. What we found that if chains are long enough, what happens? They are all connected by pi stack. So this is illustrated here. So basically, you can start at any point of any part of the chain, any chain, and then you can move kind of through this pi stacking through the entire crystal, entire thin film. And then if you increase the chain length, still you will have this percolative passes through the film, so it would not change much. However, if chains are not long enough, you don't find pi stacking between different crystallites. So for example, here in this region, A is not connected to region B by pi stacking. So therefore, the mobility decreases, and then conductivity is not that good. Okay, and then basically our conclusion in this case is that really good crystallinity is not necessarily needed. As soon as you achieve this percolative passes due by stacking between polymeric chain, you can achieve very good conductivity. Okay, so and then we also performed some more calculations. We calculated like Seeberg coefficients, and then again we found quite nice agreement with the experiment. Okay, so this would conclude my lecture because I'm kind of running out of time. And as a conclusion, I can basically say that electron transport is it's a huge subject. It's one of the most important subjects in solid state physics. There are really a lot of different directions there, and here I was able to cover only a tiny fraction of this related to conducting polymers, but this is a huge field, and still there will be much more development because there are new materials, new transport mechanisms, and I'm pretty sure that there will be much more discoveries in the future in this. And thank you very much for your attention.
Thank you very much, Igor, for doing this, and you really kept it on a level that at least I could understand it. Who doesn't have an electrical engineering background. We can take some question. We have some minutes left. Otherwise, you're free to mail Igor, of course. But is there anyone who has a short question or a comment? Okay, then I actually have Igor. You model the conductance and so on here, and I'm actually on. We are doing work on the opposite, insulation properties, and is it possible? Has it been done, or do you know if it's possible to model breakdown strength, breakdown voltage, and how would you do it?
Yeah, I think. I mean, following basically the same way. The only difference that you will find very low conductance.
Yeah, but
I think. Well, actually, I mean, this is a very interesting question. We actually studied this system. Okay, we actually look at the current passes through these systems, and we could see that current is not kind of goes homogeneously through it. Depending on some particular kind of morphology, you will kind of see this current passes. So I mean, I would guess that in isolated system, you might, I mean, you don't basically have current, but at some point, at some particular morphologies and applying voltage, you can basically get this current percolative path, which would correspond to this breakout.
Yeah, I mean, one observe electrical trees and also water trees through insulation materials. So it's like channels that are developed, which are with electric trees, they are empty, sort of. So it's like holes going through the material. But I was wondering if one with the theories that exist today can predict the voltage where the whole system becomes, at least locally, very. It's like the thunder strikes.
My answer is that if you're able to model sufficiently large system, I mean, this is very important because kind of in this our modeling, we did so-called all atomistic molecular dynamics modeling. This means that we could not go for large samples. Instead, we kind of made kind of computational many different samples and then average it over them. So here, I believe that to answer your question, you really need to go to kind of coarse-grained simulations to computationally perform morphology calculation for large samples. And then if you perform morphology calculation correctly, I believe that we will be able to see these effects eventually.
Do we have anyone else who wants to say something, ask a question or comment?
At least I would like to say that it was a very, very interesting presentation, and we are very, very happy that you gave this speech.
Thank you.
One thing that would be interesting to simulate with your methods is, for instance, to see if you would gradually increase the degree of oxidation in a polymeric system. Would you get would you get an optimum in conductance, or would it be a gradual increase or decrease?
Mm-hmm. I think this is a very important question because indeed mobility would certainly strongly depend on the degree of oxidation. I mean, we thought about this, and this is a complex question because degree of oxidation would affect not only kind of mutual position of kind of these states, but also it affects the density of states.
Yes.
So this, but I mean, certainly it's possible, and this is really a very interesting question, and it would be really interesting to do this. So I fully agree with you.
Yes, and this is something that we might speak more about more personally.
Okay.
Later on.
Yeah, thank you for the question.
Thank you.
Okay, so yes, I will create a PDF files, and then what shall I do? Probably I can send it to Linda or what?
That would be good if Linda.
Or to Mikhail or whatever. Yeah.
Is it okay, Linda, that you?
Yeah, sure, absolutely. And the presentation the recording of the presentation will be available at Research and WWSC.
Okay, I think everybody wants to prepare for a weekend. So if there's no one else raising their hand or anything, then I thank you a lot, Igor, for doing this, and yeah, have a great weekend, all of us.
Okay, thank you very much. Thank you for your interest, and goodbye. Have a good weekend to everyone.
Thanks, Igor.
Bye bye.
Thanks, Linda, also.
Thank you.
Goodbye.